standby. Sker booster. Fueling complete.
I'm here with Skov Larsen, who's the flight for today, and I'm going to ask a few questions about the objectives of these tests that we're witnessing. This morning the objectives or the tests were changed for today. Can you tell me a little bit about why?
Yes, we changed a setup on the test stand, which is the system that measures the mass of liquid oxygen we put into the LOX tank. We had some very troublesome readings because of that cryogenic cold LOX. Many things contract considerably, and metal and measurements start to behave a little odd. So we had to revise our entire LOX measurement system. And first of all, we were evaluating this today with a stop after the LOX fueling, so that we could simply measure how much the LOX measurement bounced around. And it bounced actually quite little. We were down to less than half a kilo up and down. So it looks like we have a very good LOX mass measurement. Now, the reason why we really wanted to improve this system is that the fuel oxidizer ratio, that is the ratio between the fuel and the liquid oxygen we put into the engine, we need to get this ratio very correct, otherwise the engine will not burn in an optimum way. And because we had so huge problems with measuring this LOX amount correctly, we have actually been a little bit in the dark with the fuel oxidizer relationship for some time now. So the first test we're doing today is doing another of these 7-second standard burns we've done in pressure blowdown mode, and the objective is to make sure that we get the fuel oxidizer ratio correct this time. We might have to change or adjust the tank pressure slightly, but we are crunching numbers right now to see if we got the fuel oxidizer ratio of 1.3 correct.
Okay, so just to go back to the problems with the last readings, how do you know that there was actually problems with the measurements?
It showed itself in many different ways. In some cases we would see a negative mass of up to minus 5 kilograms of LOX while we were filling the LOX tank, and that simply doesn't make any sense. Okay. So and we've had experiences where we stopped the LOX fueling and the LOX mass settled at some point. Then we gently just pushed and wriggled the LOX tank a bit, and suddenly the LOX measurement measured something completely different.
So what changes have you made to the LOX tank to change?
Well, basically we made one change, which was we have a load cell for electrically measuring the weight of the entire tank plus the contents. That was originally at the bottom below the tank. We have now moved it so that the tank is actually suspended through a piece of steel wire, which is good for both torsional moment and temperature insulation. So now there is a good 20 centimeters between the top of the LOX tank and the load cell. So now it's suspended and much more free in its movement.
Okay. So was there too much ethanol or LOX in the previous arrangement?
As far as I know, it looks like we had too much oxygen. Too much LOX.
And what would the consequences be if you had to fly a rocket?
We would simply gain less altitude. I'm not entirely sure how much, but the engine would be performing at the optimum design point.
Okay, perfect. So so now we've had the first test. So what's your initial impression?
That is probably going to be a little bit hard to say, because we had a minor mishap during this firing. Okay. It turns out that one wire was jogged rather abruptly, which actually knocked out part of our data logging system. So we have some data at the moment from the beginning of the burn, but we don't know entirely how much. And then we simply lost the data logging system. So at this point, the most probable next response is to do a remake of this burn.
Okay.
It looks like the engine performed flawlessly. Everything worked as it should. The booster group drained less than a cup of fuel from the fuel tank, so everything seems to have worked out just fine. The entire control system on the test rig still functioned in such a way that both main valves closed and the engine was purged from leftovers of fuel in the cooling jacket. So all that seemed to work out just fine. We just didn't get the data.
So firstly, what were wrong with the readings of the fuel oxidizer ratio for the last couple of tests?
Well, we had an issue with the way we measure the mass of propellant that is being fed into the engine. And basically it works quite well for the fuel side, but for the oxidizer side we've been seeing these fluctuations. And these are due to the way that the tank was mounted on top of a load cell, and that load cell then provides us with the delta mass that is put into the engine each second. So we changed the way that the tank was mounted. Instead of having it sitting upright on top of the load cell, we now have it hanging from the load cell. And that gives us a better result. And we've also redone the calibration. So now we are more or less we should be able to estimate this with a few % of accuracy. Now this is all well and for the tanking procedures. But when actually running the engine, of course, you have all the vibration and the acoustics and all the noise that the engine produces, which will, say, buffer the load cells during operations, and that gives us a challenge in interpreting the data that's coming out of it. But indications were that the previous tests had been running slightly LOX-rich, which in itself means that the engine is running a little hotter than we would like. And it also means that we are not fully utilizing the potential of the propellers. Of course,
but that means that the cooling cap is actually working quite well then?
Yes, that's one way of putting it, but it also means that we are not getting the full performance of the engine. So you really want to make sure that you tweak this oxidizer to fuel ratio to get to the design point of the engine to get the most performance for the amount of propellant that we are bringing up on the next year rockets. So the topic of the initial tests today have been to characterize this and get closer to the correct OF ratio. It seems like we are reaching that point. And subsequently we'll be doing the Jet Vane characterization tests. But for those tests it's also very important to have the OF ratio correct, because if we submerge the Jet Vane into a flow that is 200 Kelvin hotter than we had designed for, we're stressing those vanes more than need be. So of course we want to make sure that everything hits the performance targets that we set up.
So does that mean that we don't actually know whether the copper would be able to, the copper vane from last time would be able to sustain?
The copper would not stand a chance either way. But the graphite might have been exposed to more heat and a larger heat flux than absolutely necessary.
Okay. And what about, so what does it mean in terms of kilometers in flight to have the right ratio?
Yeah, the OF ratio is also important in that respect, of course, because if you're running very, say, ox-rich, so you're using more liquid oxygen per second than you actually designed for, you're going to end up with a reminiscence of fuel that doesn't have any oxidizers to combust with. So that will, the engine will cut out sooner than designed, and the remainder of the fuel will just be expelled without being combusted. So that could easily cost you several kilometers in altitude if you get that ratio dead wrong. So essentially we want to make sure that we can get that ratio exactly right, and in particularly for these newer, the next generation of the BPM-5s, which are in fact the flight engines, you want to make sure that we hit that target.
Okay. So that's the main objective of the test today,
as
of this morning.
Yeah, as for the initial tests. Yeah. And then comes the Jet Vane characterization. That's what we're going to see for the latter parts of the test today. We're going to do one more short burn of 7 seconds, like this one, like the one we did previously, and then we're going to do a slightly longer one where we allow the engine to transition from the operating point, or the design operating point, all the way through the chamber pressures down to the level that we would expect to see at burnout on the Nexø rocket.
Okay.
So we should see some instability, and we should hear that buzzing noise that comes along with running at suboptimal operating pressures. But because Nexø 1 is a rocket running in blowdown mode, you would expect to see this in flight as well. So we need to make sure that the engine can actually withstand that type of load, and of course that means that we have to do a test through that operating range today.
Okay. So and we haven't actually done those long tests of the BPM-5.
We did, yes, we did. We did one. We actually did two with the original BPM-5. But the first one back then, the computers cut out due to the acoustic noise, and the second one went fine. But remember that was the prototype engine, and that was coarsely built and oversized in some respects. Whereas this is the flight build, so it's we've cut out all the unnecessary weight in the engine and optimized it to the extent that we can, and we want to make sure that design can withstand that type of abuse as well.
Excellent. And what about so these are the tests that we're going to be doing before we go on to the dynamic pressurization.
Yes, and they'll come down the line today as a way of stressing the engine thermally, because of course when you are allowing the chamber pressure to vary like this, the thermal loading also varies. But if we enable the DPR feature, we're going to be running the chamber pressure fairly constant, and that means that the thermal load will also be fairly constant. So we can stress the engine somewhat more by doing that. And in the end, we're going to do a final burn on the sister engine to the one in the test tank currently, which will be the flight engine for Nexø 1. And that's going to be a short burn like the first one today, simply to do a similarity test. It's called an in-family test to prove that engine compares in performance and tolerances to the one we've been testing all day. And if that turns out to be the case, we know both engines are good.
So as I've got you, I can just ask you a little about the Jet Vane test as well. So we're going to be testing the Jet Vanes before we get onto the DPR? Or?
Yes.
Okay.
Yes. Target is that once this test is completed, the next one, we're going to be mounting the Jet Vane, and it's going to be sitting in place all through the remainder of the test today. And that is simply to get enough runtime on it to get to something that's comparable to the runtime that we will see on Nexø. The difference, though, is that we're going to be cycling it through 3 or 4 tests. So here it's going to experience being very hot, very cold, very hot, very cold a number of times. So the stress levels for this test are much beyond what it'll experience in flight, in fact.
But
so
on the other hand, it won't be hot for the same.
It won't be hot for the same duration, but the thermal cycling is what can cause graphite to crack. So if you have micro cracks and you thermally stress it, it will expand and contract somewhat. Graphite is not the most expansive, but it will to some extent, and especially the mounting interface will compress and extract on it. And if we can manage to crack it today, we'll know what the limits are. So, yeah.
And what about you've changed the geometry slightly on the Jet Vanes?
Yes, we've beefed up the profile slightly, and that has to do with the way that the flow erodes on a vane of this geometry. It erodes quite a bit at the base of the root, where the fin shape goes into the broader block at the base, and you want to add a little more mass down there, simply not to undercut the geometry of the vane. Also, we need for the latter test we weren't actuating the vane, and this time we'll be moving it plus minus 15 degrees, so it'll see a lot substantially larger shear force. So when you angle it out into the flow, it's going to be, the flow is going to try to twist it. So you need to make sure that it will withstand the braking force, and that's why we've amped it up slightly. It's going to give you a little more drag on its profile, but it's what's necessary to make it withstand the abuse that we're going to put it through. Hopefully.
And also this time it's mounted so that you can actually get the measuring on the steering force as well. Yes,
we have 2 load cells on the bottom, and they are measuring the deflection force produced when it's angled out from its neutral position. So that will give us the steering forces we use for the control algorithm. So that the data that's produced today will be input to that work.
Okay.
5, 4, 3, 2, 1.
seemed like a real success. Can you tell me you've had a look at the data?
Yes, the data looks very nice. This time we were looking for, again, the oxidized to fuel mixture ratio, and we were trying this time to get a specific pressure pair at the point where the engine transitions from pre-stage to main stage. We want to hit the optimal operating point just at that point in time, and then watch that degrade as the chamber pressure drops. Mm-hmm. And we actually hit this right on the mark, and it seems as if we got the oxidized to fuel ratio down to 1.32, and that's within 1% of what we wanted, so a few percent. So this is good enough to fly. So now we're moving on. The next test today will be a substantially longer burn, and this time we're going to introduce the Jet Vane. Yeah. So we have one Jet Vane on the setup, and this will be actuated, moving a pattern of plus minus 15 degrees throughout the test.
Okay, so this is going to be a longer burn.
Yeah, I would expect this to be around 20 seconds. That's what we're aiming at. We are prevented from going much higher in this because we've set the burst discs, the protection mechanisms on the tanks conservatively low at around 24 bars, so we can't really go beyond 24 bars and the burst disc will pop. So that limits us to about 20 seconds runtime in this setup. Okay, and the purpose of the long burn? Well, the idea is that when Nexus 1 flies, it's going to be operating in pressure blowdown mode. So the chamber will start out at our design pressure, and then the chamber pressure is going to drop right through the burn from 15 bars down to about 7. And that means that you're actually moving or transitioning the engine through all its resonant modes that lies in that region. And imagine, think about it as a long tube, like an organ pipe, so to speak. So an organ pipe, of course, if you blow air into one end, it'll resonate at certain frequencies, or one particular frequency especially. So here we're going to be exciting a couple of these frequencies as we move down the pressure envelope. So you're going to see this engine is going to be screeching and making a lot of noise and a lot of vibration. But this is all part of the qualification because it has to be able to withstand this in flight. And of course the Jet Vane has to as well. So this is, think of it as a stress test of the system, both of the engine but also of the jet.
Okay, so this is going to be the noisy test?
This is going to be the noisy test of the day, yes.
And if anything goes wrong?
If anything goes wrong, it'll probably be today. Be this burn today. So if shrapnel comes flying, we know why.
We'll be hiding in the bunker.
Yes. So that's a good way to go. But essentially, I wouldn't suspect anything to go dramatically wrong. One never knows, though. This is a flight build. In particular, the manifold connection of the engine, the way we feed the ethanol into the cooling cap, is a little different on the flight engine than on the prototype engine we tested before, and we want to make sure that this is not a weak spot. So this is one of the points when this test is completed, we're going to be inspecting that particular joint to see if we see any cracks or anything of that nature in that joint. That would be the weakest spot on the engine for this set. So there are different things we're looking for, and we want to make sure that we cross all the boxes before we go home today. And when this is done, hopefully the engine will be in one piece and the Vane will as well. We'll proceed with a series of more aggressive tests in the thermal range, so we'll be operating with the DPR system to maintain a more constant operating pressure and a higher heat flux, both into the engine and also into the jet.
Okay, that's good. Oh, that's also going to be a stress.
That's going to be a different type of stress. So here we're looking at mechanical stress, or thermal mechanical you might say, and the other one is more thermal on its own. So there you won't see any of the resonant modes come into play because you're keeping the chamber pressure more or less constant.
So in what way is it going to be stressing?
It's going to be stressing thermally because you're putting more heat flux into the chamber walls of the engine. So we want to make sure that we reach the equilibrium point of our cooling capacity. And similarly, the Jet Vane will sit in a constant, or more or less constant temperature environment. Yeah. Whereas for this burn, the temperature will start out high and then it will drop somewhat. It's not going to be halved or anything, but it's going to drop a few hundred kelvins throughout the burn. So that changes things a little bit.
Okay, so we'll be moving on to the more spectacular test for now.
Hopefully.
Thanks a lot for now. And we'll be moving on to the test and we'll be back later.
5, 4, 3.
Sådan der! Og ja, de har opfundet glødepærer, drenge. Roer er der stadigvæk. Roer er der stadigvæk. Roer er der.
So we're back at a static test stand, and this time with Jakob Skov Larsen again, who's the flight today. And Jakob, that was a real success. Can you run through it?
That was a tremendously successful burn we just had here. We had two objectives for this burn. First of all, we loaded it up with a very large amount of propellants, and we did a pressure blowdown run. This means that the pressure will drop rapidly through this extended 20-second burn, and it will take the engine through all of its natural vibration modes. This is why it can sometimes sound like a sort of a pipe organ at the end. It did actually give off some oscillations during just the very few last seconds of the burn. But all in all, it was a tremendous success, and it showed that the injector was stable through a very wide pressure range. This is indeed very good. The second thing that was very, very obvious was the exhaust plume. I remember looking around in the bunker and seeing people looking like there's something wrong out there. But actually the Jet Vane did exactly what it should. It shifted the exhaust plume from side to side, which is the controlling force we will use to guide the next three rockets straight up into the air. So at this test, we did also the first test of the graphite Jet Vane, and it was also very successful.
So can you show us a little about the wear and tear of it?
Yes, I can. First of all, let me try and demonstrate what the Jet Vane did. I can move it if I'm a little bit gentle here with it, and it has cooled off sufficiently. It starts out in a natural or neutral mode, where it is aligned completely with the center axis of the engine. Then it swings out to one side approximately 15 degrees, immediately swings back to the opposite side about 15 degrees, and then back to neutral, and then it stays there for a half a second, and then it repeats the process. This entire frame it's mounted on, even though it looks rather sturdy, it is actually floating on a very large ball down here, which means that the frame can actually move freely in this plane. Now, going up the frame, we have two load cells sitting up here, and they twist in opposite directions as this frame moves sideways from the forces generated by the Jet Vane in the exhaust plume. So we have recorded some data from these load cells, and we already did the calibration of the load cell just this morning. So we know and can determine very accurately what the controlling force from the Jet Vane is. And we can also determine the control force as the pressure drops in the tanks during the flight. So we get less and less controlling force the lower the pressure in the engine gets. So if we need to do a correction at a very low pressure, we need to deflect the Jet Vane much more.
All right, so then you compensate for the lower pressure.
But hopefully it will be at the lower end of the speed of sound at that point, so it should go pretty straight.
Okay, that's excellent. So, but you haven't got the data yet?
No, we will.
From these load cells?
We will have to do this in a post-processing. Okay. It will need to go through some number crunching, and we can't do this on site.
Okay. But the last thing that I noticed is that the Jet Vane itself, the graphite Jet Vane, is looking pretty good. There's a little bit of wear and tear of it, but...
Yes. The graphite is rather resilient towards extreme heat. It will erode slowly, and it's actually possible to see the beginning of the erosion, because the leading edge here, used to be completely straight. It has actually eroded slightly on the front here, and the line going down here, the geometric line in the jet vane is slightly rounded. It used to be much sharper as it is up here near the root of the jet vane. But we need this jet vane to survive for approximately 55 seconds during the next burn, and we have done about 20 right now.
Okay.
So all conclusions barred, it's looking good.
It's looking good. So I guess so now we'll be going so the next stage.
Yeah, we need to do the flight qualification of the BPM-5 engine with the serial number 3. This is the engine we are expecting to use as a flight engine in the next 1 launch campaign this summer. But we are running a little bit low on liquid oxygen, so we have decided to do the engine swap now instead of later. We would have liked to save it until our last burn, but our LOX level simply doesn't allow for it. So we are doing a record speed shift in engine, and we'll have the engine 2 swapped out with the engine 3 in a very, very short time. We'll continue to run with Jet Vane. We need to get as much running time on it as possible.
So by the end of today, you will have gone through 3 test wears, where 2 of them are the long burns.
We will go for the next test with just a short burn, a 7-second standard burn, just to qualify the flight engine, and then we will actually swap back to engine 2.
Yeah.
And then we will load it up with all the liquid oxygen we have left, and then do a DPR burn. And this means that we will keep the pressure in the propellant tanks constant throughout the burn. So we will actually get much more consistent performance and maximum pressure and thrust through the entire burn. We'll run for as many seconds as we have LOX for. So we're hoping that we are getting a little bit of a bad reading to the good side on the LOX station, so that we can run for a full 20-second burn in DPR mode.
That would be fantastic. Well, thanks a lot.
You're welcome.
Looking forward to seeing the flight motor.
Yeah, we'll be back in business in a very short time.
Perfect. Thanks for now.